Hello, so I'm Adam Phillips. I'm at Washington State University. I'm going to talk to you a little bit about a project that just finished up that's multiple criteria decision analysis of two prototype buildings in the Pacific Northwest. So we'll start kind of overview here, just start with some background motivation. We'll go pretty quick because at this point in the day, everybody kind of knows the background and motivation. Then we'll discuss the multiple criteria decision analysis that was used, because there's a bunch of them, and I used a specific one. Discuss the prototype buildings, kind of how I calculated the different input variables, and then we'll discuss the results of the analysis, kind of some conclusions that we already have come up with and where that's leading us next. So motivation really was to originally look at the kind of pros and cons of all steel versus all wood. It's a big thing where I'm at in the Pacific Northwest. And so I'd always been pitching. I had this idea probably like 4 years ago. I thought it was original, but I wasn't, obviously, of like steel timber hybrids have to be the optimal thing. So I've given this talk before, and I always say this is like the ideal steel timber hybrid, 6 Horseman Road, and then we heard from the guy today, which really made me happy because I've always thought that was like such a great blending of the materials. And so we did this study originally, though, looking at all wood or kind of all steel, because I started seeing practitioners in Seattle. It seemed like it was almost a dichotomy. They'd start and say, I'm doing all timber, and then the price comes in high, and now I have a concrete building. It's like, how did you get from one place all the way to the other place and not stop somewhere in between? And so that was kind of some of the overview. The objective here was to compare them across 3 different decision criteria, because decisions aren't made in a vacuum. Several people have talked about that today, of why they made certain choices in these different case studies. This is just trying to put quantitative numbers to the fact that several factors come into decision making. So 3 that I chose to put quantitative numbers to were seismic resiliency, life cycle impact, and construction cost. The multiple criteria decision analysis that we use is called weighted sum model. It's a very simple model. You take essentially a decision maker weight for a certain criteria, multiply by the value for that alternative, and then you sum all the criteria together to get a total score. You can either maximize that score or minimize the score. This is a minimization problem, because the ideal solution would be the smallest value for everything. So smallest dollar losses per year due to seismic threat, smallest carbon emissions, smallest cost. So it's a minimization problem. So when you see the results, keep that in mind, that this is the low score would be the most ideal score. There are other ones out there where you can actually kind of qualitatively interview people and get their weights based off of their qualitative answers. I tried to do that a little bit, but I didn't have enough sample size. So what I did is I came up with 5 different decision maker cases that kind of span the range of anybody I could think of in the construction industry. So the base case was kind of who I was talking with mostly in Seattle, where they said we kind of weigh everything, but cost is king. So that's everything weighed equally except for cost, which has 2x everything else, because cost is king. And then I went through and made everything a little bit more important at the sacrifice of something else. So you have a case where cost is the main criteria, global warming potential is the main criteria, and then this last one here is where global warming potential is kind of everything, and cost doesn't matter. Again, for where I was in the Seattle area, that's like an Amazon that just says I want net zero, and I don't really care about a cost. So the buildings, the mass timber buildings, are not designed by me. They're designed by Alex Wilson, who's at Magnuson Klemensic Associates now. The project was led by Dan Dolan, and I was part of it. But these are the mass timber buildings, a 5-story building and a 12-story building. You can see the dense configuration of 9-ply CLT walls. And these are PT, or post-tensioned rocking CLT walls, so really similar to those NERI walls that are going to be tested soon. Then we redesigned them with conventional steel framing. So it has the same overall footprint, but more of a conventional steel grid, metal deck with concrete, normal weight concrete topping slab. All the loads are kept the same. Everything else was designed the same way, but we used buckling restrained brace frames. And I designed the brace frames just using the prescriptive methodology. So we didn't run nonlinear history and kind of optimize column size. It was pure minimums from the prescriptive methodology that's in the code. So then the first kind of set of data we needed to generate was seismic resiliency data, and I don't have time to explain every analysis type, but we used ATC FEMA P58, which is a way to calculate seismic loss. And so you can see the loss curves that are up here. The way to kind of read those is it's a percentage of your loss compared to your non-structural cost given a certain spectral acceleration. And so the takeaway, which is kind of interesting, so median predicted annual loss up in the corner is the variable that we use. That's the actual number. So that's the predicted loss every year due to seismic, assuming 0% time value for money so that the building doesn't depreciate with time. You can see that the mass timber loses more, especially at the 12-story case, even though it's a peer-reviewed, or supposedly a peer-reviewed, a performance-based designed PT self-centering system. And really the reason is that these bigger hazard levels like DE and beyond DE, the loss function is much higher than the steel building would be because the drift is so high. So the building will recenter, but you break a lot of your non-structural components, so it's expensive to repair. So then we did a life cycle cost analysis following Tracy methodology. We used Athena. We did the whole 6 categories and everything else for the whole methodology, but really just the global warming potential is what we zoomed in on for this multiple criteria piece. And here's the results. Mass timber building has about 25 to 30% less carbon emissions than the steel alternative. I'm going to skip over this slide. This just means some other people have said it. You have to be careful which software you use because between software you can get different carbon results depending on the EPDs. Cost construction is very limited, so it's just the superstructure cost of the system. So very limited cost comparison. The way we kind of tried to account for some uncertainty is we varied labor rates, material rates, the cost price of CLT. We even varied like how much CLT per square foot was in the building in case somebody could say design it a little bit more efficiently because these buildings were designed by students. So we assume a practitioner could knock maybe 20% off of a student's design. And so then we came up with those 11 and averaged them. So 11 cost scenarios, we averaged them, and this is the average cost where the mass timber building is more expensive per square foot for superstructure only than the steel building. So when you pull that all together and you do your weighted sum model, you'll see there's 3 bars. There's steel, timber, and then there's a hybrid case. And so when I did just the steel timber, it didn't really create the most interesting of results. So what happened is the base case and the cost priority case were overwhelmingly steel was preferred, and the very high global warming potential case was overwhelmingly mass timber. But the case in the middle, the most interesting one, where somebody has about a 50% value on global warming potential, but they still have a 25% value on the cost of the project. So they want to be green, but they also have to have cost. They're almost neck and neck. They're almost dead even. And there wasn't a clear winner. And so we added this hybrid case, which was we just took the CLT floors from the CLT building and put them into the steel building kind of superstructure, reran the costs and the LCA and everything. And what happened is for that middle case, that case 3, the hybrid case became the preferred option. But maybe more interestingly, if you look at the other bars, the hybrid case is a close second, almost to the point where it's equally comparable across the full range. So it's not polarizing. You could have the full, I have somebody that really just wants global warming potential to be minimized, doesn't really care about cost, and it still competes with mass timber really well. And you could have the person that really just wants to prioritize cost, and it still competes with conventional steel well. It doesn't really have a weakness. It seems to appeal to everyone. And so that was one of the big things we took away. We should really research that idea more, because I just did one scenario where we just smashed the mass timber floors into the steel building. But the hybrid steel timber can really like a continuum. So you can replace glulam members, you can have steel CLT, you could have steel lateral. There's this big range of how much wood do you integrate versus how much steel do you integrate. And within that range, I think you could hit almost every decision maker that you have. And so where am I going kind of from here, building off of this work, is kind of looking at these base studies. And it was one of the things I've heard all these great case studies today, and it seems like every practicing engineer starts with, we did a base study in my office, and it seems to me that we should be able to get these done in a way where not every office has to do a base study because it's just replicating the same work. Everybody ended up coming up with roughly the same answer. And so we should be able to normalize it in such a way that we have kind of continuous functions of span and load, maybe aspect ratio of a diaphragm, and then we can kind of normalize that to get carbon per square foot for a certain delivery variable, kind of on a continuum of steel timber hybrid. And then if we match that with some type of tool to help decision makers decide what they want in terms of weighting, we can maybe get to a place where we know what the kind of most optimal hybrid design is without poking around kind of in the dark. And so that's what I'm starting with now. And then the other side is the kind of practical solutions to a concrete-less steel timber diaphragm. I know a lot of people here presented the concrete slab on top, but from a carbon perspective, if you really want to reduce the carbon in the floor, you have to get rid of the concrete. But if you want span without the weight of the concrete and without that much composite action, vibration is a nightmare. And so figuring out how do we get a concrete-less floor that's really low carbon but still keeps the span is something that I've been trying to work on lately as well. Still have a couple minutes left, but that's really kind of wraps up, I think, all I have. Thank you to AISC who supported the project. Yeah, thanks.